Good morning, everyone. Today I will be discussing an important mathematical tool that provides deep insight into the behavior of adaptive structural system, Cauchy's mean value theorem. In adaptive or smart structures such as vibration control beam or piezoelectric actuator composition, the relation between the structural response and the control effect is fundamental. Cauchy's mean value theorem offers a rigorous way to quantify the relationship by linking the instantaneous changes in response to overall changes over time. In this talk, I will show how CMVT not only provides theoretical guarantees but also serves as a practical framework for evaluating adaptation efficiency, designing optimal controllers, and validation of FEM based on dynamic simulations. The review of Cauchy's mean value theorem. Let us begin with a quick recap of Cauchy's mean value theorem, which plays a central role in linking the structural response of an adaptive system to the effort exerted by the controller. The theorem states that if we have two functions like f of t representing structural response and g of t representing the adaptive control effort, both continuous on the interval t1 and t2 and differentiable within t1, and if the derivative of g of t, g inverse of t, never becomes 0, then there must be an at least one point called c inside the interval. There must following the ratio is f of c and g of c is equals to f into t2 minus f into t1 by g into t2 minus g into t1. This means that there is always a moment in the time when the instantaneous rate of structural change matches the average rate of change across the whole duration. In physical terms, CMVT ensures that the relation between the system structural response and the control efforts cannot behave arbitrarily, it must align at some point. Engineering interpretations. Next, we define the engineering meaning of two functions involved. The function f of t correspond to the load response such as magnetic deflection and stress and store strain energy. The function gt corresponds to the adaptive effect which would actual voltage and energy consumption. The derivatives must direct engineering interpretations. F dash of t represents how rapidly the structure is experiencing and degradation of strain increase. G G dash t represents the intention rate of control input, essentially how aggressive the actuator is responding. Defining the engineering functions for an adaptive structure under dynamic loading. Example, vibration control. Function engineering variable Ft load maximum deflection stress is critical member or strain energy. Unit metric and derivative interpretation is f of t is rate of structural degradation movement. G of t adaptive effort, cumulative accelerator force or energy consumption. The unit is N or J. G dash T is instantaneous rate of control unit or power W. The ratio as adaptation efficiency. The CMVT framework transforms the analysis into a ration of effects, defining measure of adaptation efficiency. Average adaptation efficiency is equals to N average. N average is equals to f dash f of t2 minus f of t1 by g of t2 minus g of t1, meaning the total change in structural response of mod f achieved per unit of total adaptive effort over an operation. This is a measure of an overall cost effectiveness. Instantaneous sensitive n inst is equal to f of f dash of t by g dash of t, meaning the sensitivity of the structural responses of an instantaneous change is total input range. CMVT conclusion says that in the instant C is equals to n average. Application is optimal control design. CMVT provides a powerful design constraint for optimal control algorithm like linear quadratic regulation and modal predictive control. First one is setting the target ratio. The goal of control is often to minimize FT while minimizing GT. This is equivalent to designing a trajectory wherein instantaneous sensitivity of G dash of t and f dash of t, whereas to an desired constant k target. Design objective force the system to follow n inch t is equals to k target. Predictive equatum rate. If an required final state f of t2 and the allowed unknown the target average n average is fixed, the control can be used with the average ratio to calculate the required auction rate of g of t needed at each time steps in to meet the final stage goal. G dash of t is equals to 1 by n average. D dash of t is required. Finite element method FEM modeling. Practical application requires numerical simulation of an adaptive structural dynamic. First one is, so there are four types: structural modeling, dynamic analysis, and data extraction and numerical differentiation. And so let us discuss structural modeling. Develop an FEM model means finite element model of an adaptive system. Example, a small composite plate with an embedded PWD accelerators. Second one, the dynamic analysis. Apply a time independent external load P into T. Example, impact or wind, or simulate the dynamic response. Third one, data extraction. F of t, extract the time history of a maximum modeling displacement or element areas. G of t, extract the time history of an integrated control voltage force upload by accelerator calculated from the control law. Fourth one, numerical differentiation. Since simulation yield discrete data, f dash of t and g dash of t must be calculated using finite differences scheme. Example, central differential method. Validation and numerical verification. CMVT serves an crucial validation check for an fidelity of simulation and control algorithm. Verification step. Select multiple albernate time interval like TATB from the simulation result. Confirmation. For each interval numerical calculate an M average and then plot the instant F. Expected result. The plot must be intersected and constant value of n average at least once within the interval. Failure analysis. If the CMVT condition is not met, if it indicates a potential numerical error, condition difference, large time step. It suggests a violation of differentiability assumptions, often due to discontinuity in control signal G dash of t. Example, sudden switching in the control. Safety and robust implications. The CMVT framework provides metric and assessing the smoothness and stability of adaptation process. So, there are two types: non-uniformity and robust metrics. Non-metric is a control system with a highly volatile intention ratios in instance t. Large oscillations around n average indicate non-smooth or jerky control actions. This can lead to increased wear and tear on accelerators, secondary vibrations, or control chatters. Robotuse metric. The standard derivation of an instantaneous ratio of n instant over an interval of t1 and t2 can be used as Robustness metric. A lower standard deviation indicates a smoother or more predictable control applications, which is desirable or long-term structural integrity. CMVT superiorities in an adaptive system. The interest lies in the relation between the effort and the outcome, not just the outcome itself. CMVT directly qualifies the relationship. Conclusion and future work. Conclusion. The application of CMVT provides a rigorous mathematical foundation for analyzing the dynamic of adaptive load bearing structures. It moves beyond simple observations on endpoints to provide a verifiable constant on the entire application strategy. Key takeaways. CMVT guarantees existence of a point of an object of an average adaptation efficiency. It serves as a powerful tool for control law optimization by setting rate targets. If it provides a robotic numerical validations checked by dynamic simulations. Future work. Extend the framework to multiple variable settings like using vector valued functions or multi actuator systems. Investigation the stability of control law design explicitly to satisfy the CMVT conditions. N instance T is equals to K target. Thank you.